Welcome back once again. So the idea of this video came to me when I was tearing apart some of those Liebert UPSs, the bigger ones, not the small shelf ones that I showed in a previous video. The reason I scrapped them out is they were okay UPSs. They were the larger 19-inch rack space size, but they were only 700 watts. So in terms of powering computers and stuff these days, they were a little light on the power. So currently I'm using kilowatt ones for my two main computers, but I got to salvage some power silicon from it. So what you guys actually see in the shot is there's 4 curve tracers and there's a pile of power silicon. So I figure what we do is, I don't even know what this silicon is yet, so we'd go through it, take a look at it. I'd use a couple of different kinds of curve tracers on it and transistor checkers. I used most of these units in various repairs of things. The 576 in the middle and this little guy, the Atlas, were instrumental in me fixing the 5200A, the fluke with the negative 90 volt supply meltdown. The Atlas was instrumental in helping me identify what the transistors were and the transistors that were grossly failed. The 576 I needed because I had to check a 140 volt Zener diode, and this guy that runs on a AA battery or a USB connection, no way he'd be able to do 140 volts. So now, because this is the Pro, this is actually a curve tracer as well. However, it needs a computer to do that. And a couple of the more rare transistors that I had that I needed for the 5200A, primarily the 2N4888, if I remember correctly. I actually have 8 of those that are original equipment, and I ran this and stored it in, stored the curves in the software on the computer, so I have some records if I ever have to match and source new transistors. So the ability for this thing to actually be able to save and call up curve graphs is, in my mind, really powerful. I'm not sponsored by any company. Atlas didn't send me this. I bought that after watching some reviews on it. I'm not sponsored by Tektronix in any way, even though most of my videos seem to be repairing their stuff. So yeah, I mean, we have a pile of power silicon. Figured we'd identify some of this stuff, and this is actually a mix. Like here's a 3-terminal device that I have no idea what it is. Here's a 2-terminal device. I have no idea what it is. This is a pretty beefy 3-terminal device. We do have some 4-terminal devices in here that I've got mixed in for various reasons. I know what these are. These are the actual bridge rectifiers, so we won't need to test those, although I will show what they show up on the Atlas so you guys can see, but I can only test 3 legs at a time. So these will show up as diode arrays because it can't test all 4 diodes. So we'll find out what all these transistors are, and then we will, I'll pull up some spec sheets on them after we identify them. And then we'll do some testing on them. Hopefully nothing blows up. Of course, we might make some stuff blow up. Yeah, so we'll get started. So before I get too far into the video and I clear some space on the bench to make some room, because the camera right now, you guys are sitting where I normally am sitting, right in the middle of the bench. We have a Atlas DCA Pro. The DCA 75, which is a 3-terminal or silicon devices. It'll work on LEDs and diodes and things like that. So, but primarily small signal stuff. It can sanity check a power transistor for like shorts and opens and things like that. But to load test it to see if it's leaking, it just can't generate the voltages, the currents. So, primarily small signal stuff. Very useful though, because you don't need to worry about how to hook it up. You just clip the 3 leads on there and the thing figures it out itself. So very nice unit. So far the computer interface capabilities are worth the Pro features for me. In the back we have a Tektronix 576, which is arguably one of the best curve tracers ever made. Peak volts of 1500 volts. This is the guy with this test fixture, with the other test fixture that's available for this one. He's capable of doing 200 amps pulsed into the transistors to check really high power silicon. Don't have that one yet, but I've got my eyes out for a test fixture for that. They are interesting to rebuild. I have a YouTube video of actually rebuilding this one. So they've got some challenges with them. They've got some known bad parts, things like that. Check out if you're curious in the 576, check out the other YouTube video where we go through a calibration and a restoration on that one. The one I'm going to be using primarily for this video is I'm actually going to be using the 577 simply because it's just a little bit smaller. You can kind of see the size difference between the two and why the 577 is on the bench and the 576 is in the corner on the cart. The 576 is very large and it is obnoxiously heavy. The unit weighs, I think it's 76 pounds or something like that. There's a lot of iron in that unit. 577 uses a switch mode power supply and a lot less iron, so it was able to be shrunk a little bit. Now this 577 has the larger screen on it. Most of them, the plastic's in, doesn't have this extra graticule. That's, I want to say option 10, but don't quote me on that one, I could be wrong. So I'll be using this one for most of the testing. This one actually goes up to 1600 volts, so you get an additional 100 volts on this, but this is more for testing small signal and IC based components. I think it's the 178 test fixture. You can test voltage regulators, things like that, a lot of low voltage equipment. The power band on this one is on the lower voltages. You can max out the wattage on this one. On this one, it's on the higher voltages. So the primary difference between the two is there's a lot of overlap between the two units, but where the 576 differentiates itself from the 577, 576 is for power components. The 577 is for small signal components, op amps, voltage regulators, small signal transistors, things like that. That's just where they were geared to. But at the high end, no slouch either. I mean, 1600 volts max collector versus 1500 volts max collector. Still very capable unit at the top end as well. Long story short, you don't need both. I fell down a rabbit hole and ended up with both. You should see the pile of parts that I have left. I have 2 tubes and a parts unit for him. I have a D1 that I need a 177 for to get that working because the looping compensation capacitors broke. So I can't even do a calibration on that until I get a working 177 or get that cap replaced. But it's a 1600 volt air gap to variable capacitor, and it's been interesting to source. One other curve tracer you guys may not have seen is this guy over here. That is a 7CT1N. So it is a curve tracer that goes into the 7000 series scopes. It is only for small signal devices. It does not get a very high collector voltage, although it's respectable for being in a 7000 series mainframe. So the way it works is this white cable right here comes out, and you plug that in there like that, and then this cable provides horizontal sweep. This provides its own vertical amplification. You can actually flip it too. That's what this button does. Put this over here and that over there. But at the moment I have this scope set up for XY, so 2 verticals and the 7CT. If you're gonna go with a curve tracer from Tektronix, this one's a little goofy. The way the collector voltages are set and things like that. This also doesn't have any series resistors you can put in. I got it to complete the collection, in quotes, and it does work. It'll show a sweep and everything. But when it comes to curve tracers, my two daily drivers are this guy and that guy, and this guy if I need power silicon. So I'm not sure how much we'll see with that, if that'll be on the bench that much, but we'll see. So in the front of the picture, I have a couple of test fixtures for, actually these are, the nice thing about these is they are duplicates. All the test fixtures will work with the 576, the 577, and I believe they will fit the 370 and 370B, the 300 series curve tracers. We'll use these same test adapters. I don't have any of the 300 series because they are just cost prohibitive. If you look at the secondary market on those, some of them are still selling for $12,000, $15,000. They are very expensive for the 300 series. But the 300 series is also in that same vein where the TDS scopes are. So I've never had a 300 series that I've gotten to work on, so I have zero opinion on how they work, how well they work, and how well they're put together because I've never had one open. But I know a lot of the guys tend to lean towards the 576 and the 577. So a couple of the test fixtures. This is one to test. You can even test joined transistors right and left. But this will also do FETs as well. These two are actually the same. If you do find these, this bar is actually pretty important. So you're going to want to make sure if you end up with one of these, the bar is there. So they just pop in like that. Same thing on the other side. And then the switch is for testing the right or left side. It'll auto flip it. These are very useful. These are generic two-terminal devices. They're labeled diodes, but you can put resistors and everything in there. So these are good. The ones not to get these confused with are the ones that say stud diode. If it says stud diode, their spacing is different. It wouldn't be good for standard two-terminal devices, so that's something to watch out for. This is the newer version of two-terminal devices, just for the small stuff. And the nice thing about these is, with the 4 pins on them, they're Kelvin sensing. So both the 577 and the 576, they do Kelvin sensing. That is one thing that is vastly different on the 7000 series plug-in. It's only a 3-terminal, so it does not do the Kelvin sensing. And this is the only 3-terminal adapter I have for them at the moment. This is actually one of the old ones. I think this was originally for a 570. I want to say 570. Don't quote me on the number. The predecessor to the 576. Just by the design and the fact that it's bakelite. It's still in really good shape and I use it, so this will also work. So the older style terminals will also work in the newer curve tracers, but you do lose the Kelvin sense. So all the 4-terminal devices, they're all Kelvin sensing. You can even get Kelvin sensing on 5 terminals, which are for transistors. This is for a TO3. There's also a fixture for a TO66. I only have one of the TO66s. I need to get another one so I can do matching, but I haven't had to test many TO66 transistors. It's primarily been TO3. I do have a TO3 transistor. So the way it looks to test a TO3 transistor is you just put the transistor in like that, and it'll pick up collector from the pins. So the other thing to realize is when you're using one of these, and why I have some labels and they say warning interlock bypass and interlock bypass, use your head on here. If I have this set to 1500 volts and I have this transistor here, I have this switch in this position, there's 1500 volts on this metal case. So if I touch that, that goes through my feet to the ground, you can get lit up. So they are safe to use as long as you respect it and use your head. Don't do anything stupid. I.e., turn this to 1500 volts and touch it. Don't do that. This is off. Everything is dead. So the unit's not even on. It's not even plugged in. So, okay. Well, with that being said, what I will do is I'll get some of this stuff cleared away. I will put this back over on its cabinet because primarily we'll use the 577 just to save bench space. And we will go from there. Okay, I have sorted the devices in by model number. I have not looked at any spec sheets. I haven't even figured out what's going on yet. These guys over here, these are bridge rectifiers. Just the way they're marked gives it away. Plus, minus, 2 pins in the middle. AC comes in, DC comes out. These are worth salvaging out of those UPS units, as these are high current bridge rectifiers. If I remember correctly, I think this guy's 100 amps for a bridge rectifier, which is absolutely crazy. So definitely well worth saving. Their power components. A lot of these 3-terminal devices are kind of oddly marked. Obviously, they're big power components. They're stacked up, so all the ones that are at the same part number are stacked up. I have some random 3-terminal devices over here. And then we have a whole bunch of 2-terminal devices, some with heat sinks, some without. Given these are 2-terminal devices, and they're definitely silicon by the packaging, but given that these are 2-terminal devices and also the way they were configured on the boards, I'm guessing these are going to be diodes. Obviously, with a package this big and a heat sink like this, they're going to be pretty high current diodes, but I'm pretty sure these are going to be diodes. I'll get a spec sheet here in a little bit. So what I'm going to do now is I will get the Atlas. We'll hook up a couple of these and we'll just see what the Atlas says about them. And after we sort them that way, I'll pull some spec sheets and then we'll throw them on the curve tracer and see what they actually do. Let me get the camera repositioned and we'll take a look at some of these 3-terminal and 2-terminal devices. I'm not going to do the 4-terminal devices because these are bridge rectifiers. They're as common as dirt. So we'll just set those aside. But we'll definitely check out this stuff and see what we got. All these were salvaged out of some of those lower wattage UPSs that I scrapped out. But I have no idea what these parts are. But given some of the coils and things that were around them in those boards, I'm expecting some pretty heavy power components. Not necessarily lots of gain, but they should be able to handle lots of current. So definitely good to have in the parts drawer. Enough rambling from me. Let's hook some stuff up. Okay, I have a power component hooked up to the Atlas. Haven't turned the Atlas on yet. One of the great things about this Atlas tester versus the Tektronix tester is the Atlas tester obviously doesn't go up to as high a current or power, but it doesn't care how you hook it up. It will figure it out. So if I hit the on test button, it'll power up. And then it'll tell us we have a N-channel enhancement mode IGBT. So we have an insulated gate bipolar junction transistor. But then it even says cathode gate emitter because it's an IGBT. So G's gate. So it'll actually tell you the pinout on these, and that's true for anything. So I will have to save the battery, it powers down. So I will actually have to make a test fixture for the 177 because their collector base emitter, well, this one would actually test because it's collector gate emitter. So this one would actually test okay. I might have to make some short wire test fixtures for some of these other ones. We'll see what the pinouts look like. Let's check one of the 2-terminal ones here real quick. And on the 2-terminal ones, it doesn't matter. You only need to hook up 2 of the leads. And we have a diode junction. Tells us red's on the cathode and blue's on the anode. And looks like it has a 0.486 volt forward at half an amp. Or 5 milliamps, sorry, not half an amp. So if you want to see what the tester does, alright, I had to make some test fixtures. Those can be found right there. I do want to keep away from the connectors because these are actually metal, and I have the collector volts set to 100 volts, so that's why the red angry light is on. But given what the Atlas DCA Pro said, this was an IGBT. So I got the curve tracer set up. I have a 100 volts collector. I have 2 volts per division on the step generator, repeating. 5 volts on the collector, which would be 5 volts per division on the horizontal, and 20 milliamps per division on the vertical. So on the 577, the vertical control's down here, horizontal's here, step offset's there. You can see it's set to 2 volts as opposed to a current. We are repeating. I have it set to currently 30 watts. On this switch, we have step generator connected to the gate. So on these particular IGBTs, it's gate collector emitter, which is why the normal test fixtures wouldn't work, because it's collector base emitter, or drain gate source, which pinouts don't match. This is a transistor we'll test here in a little bit. So this one also is collector base emitter. When it's in the test fixture, it goes in like this. So collector, focus. There we go. Collector base emitter pops into the test fixture like that, and then you have collector base emitter for testing larger transistor packages, but those pinouts wouldn't work for an IGBT. Here we go. I'll zoom in on the screen, and we will check out what it looks like on the curve tracer. So I'll turn up the collector. You'll start seeing the voltage down here. So that'd be 5, 10, and we have conduction. So everything. Okay, figured out what was wrong. The gate lead had come off, so I wasn't getting any gate voltages into the device. So if we do this, we have 5 volts, 10 volts, 15, 20, 25 volts. And we're seeing the transistor turn on. If I give it some more testing, you will see it goes. Can you actually see that? No, not really, because all you can see is a faint line drawing up due to the fact that the camera's shutter and the curve tracer are in a weird sync mode. That's probably about to go away. Nope, camera just got more sensitive to it. So you have voltage at the bottom, current at the top. So we have the device trying to turn on, and then it does the IGBT thing and goes into a dead short. Turn up the intensity so you can see the waveform. Actually, there we go. Get that so it doesn't match up with the camera shutter. So you see it trying to turn on down here. You see it starting to turn on, and then it just goes dead short above that at above. That would be 4-ish volts on the... No, sorry, because let's zero that. There we go. So that would be, we'll call that about 1.25 volts on the base, or on the gate. And then above that, the device is just on and just kicks on. So I can vary that, because if I do this, there's 2 volts. No, sorry, it's 2 volts per test. So this is not actually giving us an accurate data. Okay, try that again. This is 2 volts per step, so we'll start turning this up. There's what sort of looks like a transistor curve. There's another transistor curve. Now, this is kind of fooling the measurement a little bit, because if you looked at this, you would say I'm on 2 volts step amplitude. I have 1, 2, and then up, but we really don't. My other curve tracer will prove that out. But then, so we have it trying to turn on, and then it just goes into the switch, dead shorts, and shorts the collector to the emitter and acts like an IGBT. So the neat thing about these was I did sneak a peek at the data sheet yesterday. I'll bring a data sheet into the camera. These things switch monstrous amounts of voltage. I think this guy's rated for 500 volts, and I think it's something like 100 amps. Like it is a ridiculous amount of power. But they're designed to be switches. They're not designed to amplify or anything like that. It's just on or off. That's why they're used in these chopper inverters, which is what this came out of. So it's very hard to get this curve, because it doesn't want to be. It wants to be off or on, and it doesn't like hanging out in this zone like a transistor would. This isn't a transistor, it's an IGBT. To go along with that, we have, we'll zoom this out. This is the graph that that the DCA Pro will do. You do need a computer to generate these graphs. So the DCA Pro hooks up to a USB connection, and then you can do VCE, or you can do IV curves of different 3-terminal devices based on how you set the software. You can see from here, I ran the graph from 1 to 10 volts. So there's actually 10 graphs in this plot, but you only see 3 lines. It's hard to see, but this is green down at the bottom. So you have green, blue, and gold, I guess. And so, but you can see the VGE of each trace at the end of the table. So from 1 to 4, the device didn't even turn on. We have full voltage, no current. At 5 volts VGE, it started to turn on, so we get a traditional transistor curve. But then above 5 volts VGE, we end up with just on. The device is just a dead short. So 6 through 10 all did the same thing. Now, some limitations. The DCA Pro really can only do about 12 volts. That's just a matter of the device is powered by a AA battery and a USB connection. Doesn't have a lot of grunt to do the heavy lifting of the power transistors. That's where this guy comes in. So for the small signal stuff, the DCA Pro is great. But if you suspect you have a leakage problem on a power device, it may not see it just because it can't generate the voltages it needs. But if I turn this back up, I don't know about you guys, but that looks pretty similar. I can blow this up a little bit by limiting that and adjusting that. So what I did there was I turned the self-limit down, and then I increased the zoom on the vertical, so now we're at 5 milliamps per division instead of 20 before. But yeah, that looks, those graphs look pretty close to each other. But what that does tell me is, because I have 2 volts per division, or sorry, 2 volts per step set, this is not the second step. This has to be the third. Yeah, the third step. due to the fact that it's got to be right in that 5-volt range before the device is off or on. So if I turn this to 1, it'll go away because I don't have enough steps generated to get up to. If I turn that up, I can get the step back. Now I'm right in the middle, so that would be right about 5 steps. There's 6 steps, and our graph is back. But we only have 1 volt per step, so it has to go six steps to get up here, and then it's got to do for the 6th step, 5 steps to get up here to the 6th step to get up here. So there's a lot of data that we're actually missing in here because it doesn't have some of the readouts and metric functions, but we have a 2019 device that plugs into a computer, a late 80s device that runs on a CRT. Both of them have their uses, just 2 separate things. Oh, in looking through the part numbers on the rest of the ICs that I pulled out, they're all IGBTs, so they're all going to do the same graphs. They're all going to do the same thing, except for these. These are high current, fast switching rectifier diodes. These were actually really valuable to get out of that, to salvage out of those curve tracers, so I'm real happy I got these. But let's get some more semiconductor devices, and we'll play around with the curve tracer and the DCA Pro as well. Well, here's how some devices can differ. I ran the test again with the IGBT that I had hooked up to the curve tracer. So this was the other IGBT, and then this was the one that I had hooked up to the curve tracer. So right around 5.5 volts is where it was trying to turn on, and then everything else was on. So the DC Pro matches very closely to what the 576 was giving us. One other way that I used the DC Pro was when I was rebuilding the Fluke 5200A. I had a FN2888 transistor that went bad that I was trying to replace, and I've come to find out those are discontinued transistors, and there's no replacement in the same model number. What I was able to do, I was able to source some of those from a seller overseas. I think it was Scotland, actually, that where the gentleman was that had some. They got stuck up in customs for a while, and I had to wait on them. But when I got them, I ended up with 6 of them, and I used the DCA Pro to do a many data point map. This is a very large data point. You can see a little bit of wiggle in here. This is probably just noise in the device, but I asked it to do a very granular inspection of those particular transistors and get a plot. Now the other thing, given that the DCA Pro is on computer, I was able to save these. So I have a record of some actual curves from that specific device. So if I ever run into it again, I can pull these up. I sampled all 8 of them. It took about a half hour to draw this graph because I told it to do, I think it was 1,000 points per line or something just stupid like that. But I just let it sit there and cook for a while, and it was on a PC, and I ended up with these charts. So I sampled all 8, I saved all 8, and I have all 8 in my library now. So if I ever need to replace another one, I can reference this, run another test on a device, and see how closely it stacks up with the exact same settings that I did with this test. So it'll allow me to test transistors even if I can't even find the device, because I have a sample and record of the curves from that actual device. And this will work with anything small signal. Won't work with anything much higher than 12 volts, at least that I've seen so far. But yeah, it's good to be able to compare transistors to each other without actually having any of the transistors. Now I did put those 6 rare transistors in stock, so I haven't had to use them for anything, but they'll probably be just reference parts going forward so I can compare things to, so I can compare transistors to each other if I need a modern replacement. But that being said, let's set up the curve tracer again for one of the most generic transistors on the planet, as I have, there's about 500 of them in here. Kind of see them all in there. This is probably one of the most jelly bean transistors out there. This is a 2N3904. 4 or 6. 2N3904. So this is the NPN version. The 6 is the PNP version. So we're on NPN. I dropped it back down to 6.5 volts. This is a transistor, so we actually need current. So let's give it 50 microamps per step. Collector volts will go down to, we're going to max out at 6. So half a volt per division. And on the vertical, let's look at something like milliamp. That's set to fast. We're 0. Polarity is normal. For the step generator, everything looks good. Let's turn it up and see what happens. Oh, I have to turn the transistor on. Okay, well, so the transistor's off, so we'll turn it on. And if you saw it, the line jumped a little bit. I'll zoom in on that. Right there. So see how it goes up just a little bit when I turn it on? We don't have any steps yet, so if I turn this up, we have some steps now. However, we need to zoom in on our vertical, so let's pull this down a bit. And there is our set of transistor curves. That's a full set of 10 curves. The shutter speed in the camera, I can see it okay. Shutter speed in the camera is a little wonky. But if I do this, it's half a volt, 1 volt, 1.5, 2, 2.5, 3. Drop that down to 0.6 watts, 3.5, 4, 4.5, 6. And as you can see right at the tail end, it's starting to curl up a little bit, which means we're starting to get into breakdown of the transistor. So if I bring the vertical current down and I give it more base current, we'll get better amplification on the transistor. So what I just did there was I added, so every step is 200 milliamps additional current on the base. So nothing, 200 milliamps, 400 milliamps, 600 milliamps, 800 milliamps. No, I'm sorry, 0.2 milliamps. So it's 0, 200 nanoamps, 400 nanoamps, 600 nanoamps, 800 nanoamps, 1 milliamp, 1.2 milliamp, 1.4 milliamp, 1.6 milliamp, 1.8 milliamp, 2 milliamps. Now I can slow that down by decreasing the amount of steps, which will make the display more solid, just because you don't have the flicker of the CRT with the camera. Now we could also check when this particular transistor breaks down. So let's do that. If I turn this off, bring this back down, put that at 25 volts. What we're going to do is we're going to open the base, and we're going to watch for about 10. Oh, no, base is open, so we're not even using that. So the collector volts are going to be We'll do it for 5 volts. And the vertical, we actually want to look at, let's look at 0.2 microamps. When does this transistor leak at 0.2 microamps? And now what we'll do is we'll wind this up. 5. Whoop, right there. We have current. So this transistor is actually breaking down. It can no longer hold the collector current back. We're sitting at 2.2 microamps of division, so 200 nanoamps. So that'd be 2, 4, 6, 8, 10. So right there at 1 nanoamp or 1 microamp. Base is open, and so actually let me ground the base. We'll short the base to ground. Base is shorted. So right now B and E are shorted via this knob right here. And I have it currently set to 5 volts of division, but I'm not getting that much, so we'll back it off a little bit. Nope, too far. So it's now 1 volt per division, so 1, 2, 3, 4, 5, 6, 7, almost 8. So 7, right about 7.8 volts is where this actually breaks down. That breaks down for that transistor. I'd have to look at the data sheet to see if that's any good, but we'll take a look at that. Okay, so I was being kind of unfair to the 2N3904. I had the current per division set way too high, or way too low. So this is saying the off characteristics are collector emitter breakdown, and they actually want, I will set it to 0.5. So what they want me to achieve is, okay, after figuring out what's wrong, always trust your instruments more than yourself. And the transistor in backwards. I was wondering why it was indicating way too low, because the spec sheet says it's supposed to have a collector emitter breakdown voltage of 40 volts DC. It was reading about 6. Well, the emitter base breakdown voltage is about 6. So, didn't get the pin out right. Essentially had the transistor in backwards. So now I have the base terminal shorted to the emitter, because the emitter is grounded and the base terminal shorted to the emitter. With the knob, we're set to 0.5 milliamps on the vertical. And I'm supposed to go to 10 volts. We have 100 volts on the collector. We have 10 volts on the horizontal. So this is going to be 10, 20, 30, 40, 50, 60. Anytime now it's going to start. Oh, there it goes. Okay, so this is actually a way overachiever. So we have 10. I'm sorry, I had to actually up it. So it's 20, 40, 60. So anytime after this, and we're in spec. 80, 100. And there we go. We have current. And actually it maxes out. Oh, I could do that. I could give it some more power. There is 0.5 milliamp. And that's actually maxed out the 100 volt range at 9 watts. So That's well under what the spec says. It's a very nice transistor. So that's good. Without even moving it, we'll go down here, flip this down to emitter to base breakdown. Hit this again. It wants far less current. Emitter to base breakdown voltage is 10 microamps. So we have one block. So when we hit one block, we will be at the rated breakdown voltage, 25 volts max, to 1 volt on the horizontal, 1 volt, 2 volts, 3 volts, 4 volts, 5 volts, 6. Oh, right there. So this is actually an overachiever as well. So 1, 2, 3, 4, 5, 6, 7, and a half, and it says it wants breakdown 1 division. We're bouncing right over 1 division. So there's our base to emitter breakdown, or I'm sorry, emitter to base breakdown, reverse bias of the junction. So this guy is even within spec as well. And because of the current limiting of the 577, we should not have actually damaged the transistor. So let's do 5 volts of division. Get some gain. Emitter, or no, grounded emitter, base to step gen. And so we have, so everything's all set up now. We're actually doing a transistor function test. I have 4 steps, 10 milliamps a step, 5 volts collector volts, 2 milliamps on the vertical. So we have 5, 10, 15, 20, 25, no breakdown, go up to, now it's 10 volts, 10, 20, 30, 40, and we're seeing to start it curl up here, 50, there it goes. So the transistor's saturated at that point, so everything's good. So you'd want to use this transistor back here in this region if you wanted to use it in the linear region. If not, it's a switch, because there it goes, it's on and it's up, but that's 10, 20, 30, 40, 55 volts of division, or 55 volts total, because it's 10 volts of division. So that is a 3902. Now the neat thing about the curve tracer is, actually I'll hook this up to the Atlas and I will let it plot some graphs, and when that gets done I'll be back. Well, we have curves from the exact same device. I've set up the 577 and the DCA Pro the exact same way, same parameters, same everything. And I ran a 10 curve test. This is all the way up, so we're getting 10 steps. We ran 10 curves. Now on this one, the initial 2 in the beginning, actually up until, the initial 3, they just saturated the transistor. The transistor just turned fully on and didn't do anything. But so yeah, you actually have a little bit more sensitivity in the 577 than the DCA Pro. However, vintage piece of lab gear that was in a completely different price class, $150 transistor tester, which is dynamic, which you don't care the way you hook it up, and it can plot curves for you with a computer. Very nice unit, especially with the curve tracing function on the computer and being able to store curves. Wonderful unit. I will be using both regularly in the lab, I'm sure. Before I got the curve tracers fixed, I used that to actually figure out if a couple of my transistors were blown up in the 5200A. So turns out they were. Now, where I did run into a problem in the 5200A was one of the power transistors, the big guys, was leaking. And it wasn't leaking bad enough where the DCA had enough current to show it. So the DCA was reading the transistor as good. It was not a good transistor. The 577 or the 576, in that case I used a 576, it showed the transistor as bad, so I was able to fix it. Next thing I'm going to do is I'm actually going to heat up a soldering iron, and because the DCA won't show this very well because it's digital and it does sampling, but because this is analog, I can show what happens to a transistor when it gets hot. So what we'll do, heat up this soldering iron real quick. I'll zoom into the screen. I'm going to use the same parameters, probably. Yeah, I'll use the same parameters. We'll bring the tests down so they're more stable. And then what I'm going to do is I'm going to use the offset just to line up the middle of the middle trace. Actually, let's do the top trace. We're going to line up the top trace with that horizontal radicule line right there. So keep an eye on this area of the screen when I use the soldering iron and I heat up this transistor. There it goes. Take the soldering iron off. It's slowly coming back down as the junctions cool back off. We'll do that one more time. I'm going to touch the transistor now. And all I'm doing is touching the top of the transistor with a soldering iron. So as the transistor heats up, this starts climbing. And what that does is that telling us it's drawing more current. So as the transistor gets hotter, it passes more current because the physical characteristics of the transistor change. And that can cause some runaways. So what I'll do now is I will get one of those power diodes, and let's see what the breakdown voltage is in that power diode. Okay, so I got the power diode hooked up down there, and this tells us that I hooked it up the correct way. So we're forward biasing the diode, so we turn on very quickly, and then we just have a short circuit. So what I need to do is I actually need to turn the diode around. And we're going to do some breakdown voltage. I want to test breakdown current. Well, let's test 20 microamps of breakdown current per division. Turn this way up to 400 volts. And we're 20 volts of division on the collector. So 20, 40, 60, 80, 1, 20, 40, 60, 80, 2. So that's 200 volts. No breakdown yet. $100, $200, $300, $400, still no breakdown. And I have to 100, 2, 3, 4, 5, 6. Oh, right there. So That's 600, right about 600 and call it 30 volts. So these diodes, actually, it is a diode. These diodes have a breakdown voltage of 630 volts, and then once it hits, it just goes dead short. So these are actually some pretty stout diodes. The other thing on these diodes is they're fast because they're rectifier diodes. They're high current rectifier diodes, so they're quick and they have some pretty insane breakdown voltages. So I'm about to touch the diode again just to be sure, because I had this turned all the way up to 1600 volts collector. It's all the way back down to 6. The variables all the way down to 0, and the 177 is out of the test fixture simply because I don't want to touch 1600 volts. Now, another thing to be careful of on these devices is this back plate. All of these IGBTs and diodes and everything, they needed insulators due to the fact that one of these terminals is shorted to this back plate. So if I had this hooked up to the curve tracer and I touched it like this, I could get a shock off of that because this back plate is shorted to one of these terminals. You can find that out with an ohm meter. You just ohm it out and it'll tell you which one it is. Now the diodes, they don't have an insulator because ground was the reference for the heatsink. So these heatsinks weren't hot. These heatsinks were actually soldered into the board. So these things were okay. So that's IGBTs, that's transistors. We'll do a power transistor here real quick. Actually, we'll compare a power transistor to a small signal transistor. I still got that 3904 out. So what I'll do is I'll put a power transistor on this side, and I'll put a small signal transistor on this side. We'll use the same settings, and then we'll compare the results on the screen up here. Because one of the neat things about these is for matching, all I got to do is that, and it'll drive both of them the same way. So let me get that set up, and I'll be back. Okay, I have the small signal transistor set in. It's our 2N3904. I also have a power transistor in here. It's a 2N3055. Both of them are NPN, and I have the curve tracer set up the same way. So what I'll do is we'll go to the 2N3904, and let's add some steps to get it to the top of the screen. So we'll put the last trace at the very top of the screen. So the difference between a small signal transistor and a power transistor, I'll just flip it over. You can see with the exact same settings, we top out not even up here. We're just barely over half of the screen. That's the main difference. Is power transistors, they'll actually have voltage holding for days, very high collector withstanding voltages. You just don't get the gain out of them. This is actually really good for a power transistor. I have an older power transistor right here, which is an RCA 2N5240. This is actually a vintage one. This isn't a new 2N5240. This is an old one. So what I'll do is I will pull that out. We'll just put this RCA on the test fixture. Also, it is worth noting when you're working on transistors, the outer case is the collector. So whatever the collector voltage is on the transistor, that's exposed on this area. So if I turn this all the way up to 1600 volts, there's 1600 volts in this case. Do not touch this when it's in circuit, when it's on, everything. The only reason I'm touching it right now is the collector voltage is down at 6 volts, and my test is off, so I'm not sending any voltage here at the moment. But these cases are live, both in NPN and PNP transistors, so do not touch these metal cases when the transistor is in service and the circuit is energized. So if we take a look, we're still here, we're still right at the top, everything looks good. This is our small signal transistor on the left. Flip it over to the right. Uh-oh, it looks bad. Well, let me zoom in on the gain a little bit. It's not bad. It's transistor. It's just no gain. This particular transistor has an HFE, which is the gain, has an HFE of 18. This 2N3906 has an HFE of 187. This guy is actually an overachiever. This guy's an overachiever for a power transistor. He's got an HFE of 97, which isn't too bad for power silicon. So turn that back down, flip it back over. See, we're still right up at the top. Flip back to the power silicon, and it's a transistor, but there's just no gain whatsoever. It's just dead. Well, thanks for stopping by the lab today and checking out, playing with some power silicon that I've harvested out of some of those UPS units, and checking out the DCA Pro transistor tester and curve tracer, and also the playing around with the 577 from Tektronix, curve tracing, and checking out some of the IGBTs. If you guys have any questions, comments, please leave them in the comment section below. I read all the comments. Thanks a lot, and have a good one. Bye for now.